All right, there may be more people trickling in later on, but let's get started. So it's a pleasure to introduce Professor Anthony Pullen from NYU. Anthony's research is all about combining different kinds of large-scale structured data sets to make cosmological inferences. And so today he'll be telling us about doing this with line and test mapping surveys, including Exclaim, for which he's the science lead. So Anthony, feel free to get started whenever you're ready.
Thank you, Dongwoo. Share my screen. Okay, can everyone see the screen? Great. Thank you for inviting me to give a talk. I definitely appreciate Dongwoo, who's confirmed, who's I've known him from before, obviously, but also conferring with me just to get set up here. So thank you, Dongwoo. So today I'm excited to talk about line intensity mapping. And I taught us talk modeling and analysis in the precision area. The goal of this talk is basically to show you just the work that me and my group at NYU have been working on in collaboration with Goddard Space Flight Center in order to both model the several lines that will be used for intensity mapping surveys. So at CITA, CITA is very much a part of the intensity mapping game. So there's not much I need to introduce or that, but I'm just happy to be able to present my work and my part and my group's part in helping to do that work. So and this is on the bottom left, you see a list of my collaborators. I especially want to highlight a few. Patrick Brees, who is a postdoc at CITA, who's now postdoc at NYU, and we're happy to have him, as well as Shengxi Yang, who is finished. He's done a lot. He's involved in a lot of the work with this talk, and is especially soon was about to graduate and will be moving to a postdoc at Carnegie Observatories in Pasadena. So this is just a brief outline of my talk. First, I'll just start off. I'll speed through the line intensity mapping primer just because most of you guys have seen this hundreds of times before. Also, and then after that, I'll discuss my work, specifically working on a semianolytic model to model lines using properties of galaxy evolution in a self-consistent way. Then third, I'll talk about Explain, which is the survey that Dongwoo mentioned I'm the science lead for, and what our goals are and what we expect to be able to learn from Explain. And then finally, I'll talk about some projects that I've been doing with some of my other students on using line intensity mapping and applying it to in cosmological settings. So that's what I'll be focused on today. So first of all, line intensity mapping. So just because we need somewhere to start. We know that after the recombination, when the cosmic microwave background photons decouple from neutral atoms, we knew that that basically universe was basically it was a dark place. It was the dark ages. Didn't have there was no star formation back then. And then it was about 400 million years after the Big Bang when galaxies were able to collapse enough to form the first stars, and this is what began what's known as the cosmic dawn. And at this point, what you basically had from then on is you had UV photons, which were emitted from these stars, which were able to convert the intergalactic medium from a neutral state to an ionized state, to an epoch that we call reionization. And it's and as these stars were formed, future generations of stars would be able to seed metals into the galaxies that were forming, and those basically turn into, as galaxies form, they're able to turn more into the large-scale structure we see today. So that's the general picture, but there are specific things that we'd like to learn more about. For one, we like to understand star formation. Specifically, if you see on this the famous Madal plot, you notice that at redshifts less than 2, as redshifts go less than 2, the star formation rate goes from an increasing to decreasing state, even though the clustering of dark matter, which seeds the formation of stars, that still continues to increase. Of course, in particular, the fact that at low redshifts, you get like 100 times difference between the amount of, you get 100 times increase in dark matter, but you get a reduction in star formation. We think this is seeded mainly by stellar feedback, but one thing that we like to know is really understand the mechanisms behind stellar feedback. And so this is a main puzzle that we would like to learn more about. We also have the issue of missing galaxies. So this is actually this is a plot that was put together by Patrick Brees. And so we know that the Very Large Array is one of the biggest telescopes we have in order to observe very distant bright galaxies. But even if you look on here, you see that these red dots represent the galaxies that we can observe from the for using the VLA, whereas the dark gray dots are what the galaxies you actually expect to be there. And so you see here that we're using big, large telescopes, but with large apertures, with very large apertures, we still tend to miss many sources of emission that can basically mean that we don't get a full picture of the sort of the galactic archaeology history of the universe. One other thing that I like to bring up is from a recent paper by Gregor Popping that looked at basically where molecular hydrogen was. So molecular hydrogen is a very is a molecule that has a large role in star formation. And one thing you see here is that on this curve, what you see is that while based on the galaxies that can actually be observed from the aspect survey, which is a sort of a subset of the ALMA survey. Is a galaxy survey using the ALMA telescope. You see that this curve, this dashed curve here represents the amount, basically the density of hydrogen as estimated from the galaxies that could be observed by aspects or as a function of redshift, whereas these gray bands here represent what the total amount of hydrogen density that you'd actually expect from the aspects volume, and this is as determined using the illustrious TNG simulation. And so, as you see here, galaxy surveys alone would not capture most of the molecular hydrogen. And particularly, this is true at large redshifts, where you see a very large amount between the difference between the amount of total molecular hydrogen versus the amount that's found in galaxies that we can currently observe. And so this is also an issue that we want to resolve. And intensity mapping is the main tool that was one of the major tools that people hope to be able to resolve this. In particular, the intensity mapping is the idea that you are measuring the aggregate intensity in large 2D pixels and multiple frequencies. And the idea is that sort of like each plane here that you measure on the sky of full line intensity is a measurement of the clustering in each of these redshifts, and you can put all the information together to form a 3D volume of intensity. And it will look something like this: is where you have where you can see on the sky what fluctuations in intensity are, but also you can look out into different frequencies in order to map redshifts and distances across time. And so this is important because you can use this to do both cosmology, but you can also use it to do astrophysics and just being able to see all the sources of star formation throughout cosmic time. The key thing is you're sacrificing angular resolution because you're not detecting individual galaxies, but you're seeing the full volume. And so that's much more than you could, with much less resources than you would actually, particularly time resources than you would need if you're trying to do this using a large aperture telescope. And one thing also too is that with mapping large areas, one advantage of that is that you're actually reducing cosmic variance that you would normally have to deal with because most of the galaxy surveys that normally do this type of work are over very small patches where cosmic variance is a big word. And so this, by being able to do a large area using intensity mapping survey, you're able to sidestep that problem. So there are many reasons why you want to do intensity mapping: by probes of star formation, probes of ionization in the stellar medium, and in stellar medium, looking at the constituents of different gases and regions that make up the interstellar medium, as well as being able to do cosmology, particularly probes of GR and inflation are very advantageous for intensity mapping because those tend to have distinct effects on very large scales, where being able to do a large volume survey with intensity mapping will be very advantageous. One thing I forgot to mention in the beginning, please feel free to ask questions. We're kind of used to this at NYU, so feel free to, if you feel comfortable, feel free to just go ahead and ask questions. during the talk, or wait for the end, whichever works for you. I doubt any of you don't know what a power spectrum is, but we measure two types of statistics with intensity mapping mainly. One is the power spectrum. So that's one, and that just measures the clustering, both the clustering on small scales as well as the clustering on large scales. And whereas on the small scales, we have shot noise that mainly measures the populations of sources of emission. And then also another statistic that we try to model is also what's known as the voxel intensity distribution, also developed by, particularly for intensity mapping, developed by pioneered by Patrick Brees. And the idea being is that while the power spectrum will measure the first and second moments of the luminosity function, while also measuring the clustering, the voxel intensity distribution will measure the full luminosity function distribution, while not directly measuring clustering. So the idea is that by putting both types of statistics together, you can actually begin to break degeneracy between the astrophysics of galaxies versus the cosmology side, in order to do both. And so that's why much of my work actually is interested in modeling. Lately has been modeling both in order to promote its use in both in line intensity mapping science. Okay, so that was the introduction. Now I want to talk about multi-line intensity mapping models that we've been working on. So there are many surveys out there. So intensity mapping, they're really the amount of lines that you might use never ends, but there are many that have been developed over the past, I guess, 20 years or so, and have been developed all the way to the point of now we're sort of on the cusp of different intensity surveys that are now running, including, of course, CoMap is a huge part of that, and is the one that I think people are most excited to see the results from soon. But also there are other ones that are coming down the pike, including Explain, which I'm going to talk about today, as well as Mini 21, which is mapping CO and C2, as well as many other surveys measuring CO, as well as of course 21 centimeter, like Hera, and so in China. So there's many groups. I like how our community is a very broad community, expanding over various areas, and everyone is really contributing. It's sort of like the first days of the CNB, I feel, in that there are many groups who are working towards common goals. And I think one thing that's even special about this is because we're looking at different lines. Different lines have different properties and trace different parts of galaxies. And so particularly on the astrophysics side, you're going to see being able to use multiple lines together, you'll get a result that's better than the sum of its parts. And so that's something that, and so the idea of modeling multiple lines simultaneously is something that I've been very interested in. So just as a review, so each of the lines sort of map different constituents of, particularly talking about galaxy evolution. So with the 21 centimeter, you're mainly mapping neutral hydrogen, and you can map this both in the intergalactic medium as well as with the neutral hydrogen, trace neutral hydrogen inside galaxies. You're also mapping and with CO, it's a good tracer of H2 gas, particularly the 1 to 0 line has the best correlations with molecular hydrogen, which again is it's a tracer of star formation. It's one of the initial galaxies that I need to create stars. C2 is mainly tracing gas in the interstellar medium, particularly in hot ionized regions. And it's going to be a great way to probe star formation. And then finally, Lyman alpha is interesting because it's traces star formation in neutral hydrogen, both within and in the galactic medium. And so particularly for these lines, which now are developing C2, but particularly Lyman alpha, that's going to trace neutral hydrogen in the galactic medium, as well as star formation. It's a line that's going to be traced by. So Hyrax is going to map this line, and it could be very useful, and I believe it will be very useful in the future. So just wanted to do a shameless plug for one of my earlier projects with, in particular, my student, Sheng-Chi Yang. So one thing we worked on is being able to constrain a model for C2 emission. And so what we did was we basically took Planck Planck maps in sort of the what do you call it, the infrared, some of the on the infrared regime, and we cross-correlated those with quasars from Planck around redshift 2 to 3. The idea being that one of the maps, by cross-correlating each of the maps with the same galaxies, the goal of that would be to, excuse me, the idea of that being that you should that those galaxies should only cross-correlate with C2 at the same ratios as the quasars. And so the idea is we wanted to use multiple maps because you had other foregrounds, particularly the CIB, which is also a correlated foreground, which is a challenge. We use those cross correlations in order to have a model both for the CIB and the C2, which allowed us to isolate the C2. And so we use this. By using this, we were able to make a constraint for excess emission, which could be explained by C2 emission at redshifts 2 to 3, which is exciting. It's actually there are models that do fit with these. However, we feel like we're not 100% confident yet that this is really C2. One thing is that the models that do match with this type of emission tend to predict too much star formation, and so the VC, and so that's sort of an issue with that. And so there may be ways to sort of get around it if you have more hydrogen, than we expect. But yeah, that's neutral molecular hydrogen we expect. But it's not really an ideal situation. So we're still one other possibility, of course, is that there's still some contamination with foregrounds that it's causing some of the excess, particularly for CIB. If, for example, the redshift, it's possible that the redshift was different than we expect, that could have affected the model. So we're hoping that with future surveys like Exclaim, they should do a better job of remove foregrounds, particularly because while Planck is a broadband survey, it's available, so that's why we used it. It is also a broadband survey, and so that's one issue with trying to do that. We're trying to remove foregrounds, it makes it much more difficult. But with upcoming surveys that have higher spectral resolution like Exclaim, it should be able to give a definitive word on removing those foregrounds and seeing if what's left is consistent with our current measurement of C2, or if it's at a lower measurement, or if we detect it at all. So that's something that I'm really looking forward to, and actually one of the main motivations for Exclaim. Any questions so far?
Okay. Oh yeah, Anthony. So for this excess that you're maybe seeing, just to understand this, I mean, like, so the cross correlation, I guess, will be proportional to like it'll be proportional to the overall emission, but also proportional to the bias of these objects. Mm-hmm. So how do you how do you disentangle those two factors?
Right. Good question. So we actually don't in this project. What we do is we have what we did was we have a prediction for what we actually detected, and we showed this in the paper, is that we have a measurement of bias times intensity, and then we insert a model for a typical bias, what we'd expect based on the Tinker halo mass function, and so we use that in order to get an intensity, but we don't directly measure the intensity. That's correct.
Oh, okay, I see. Okay, all right, thanks.
Okay. So one thing is we want to improve the the intensity models for different lines, not just for C2, but also CO and many of the other lines. One thing we're thinking about is just that, and typically what we do is we use what are known as semianalytic models in order to do this. So the goal is that many of the models that are used in intensity mapping studies, they either develop from scaling relations where they peg it off of a measurement from low redshifts and try to extrapolate it upward, or is done from simulations where the simulations are limited over very small volumes. And so what we want to do is, and that's which is necessary because you have a situation like you have a simulation like Illustrious, which can map over a cubic gigaparsec a volume, but the problem is it takes about a year to make a simulation, an order of a year to make a simulation. And so what we wanted to do was, and so that makes it difficult. So what we wanted to do was see a shortcut around that. And so semianalytic models provide that. The idea being that it's not a perfect solution, but it's a pretty good one. The idea is that you can use simulations to sort of calibrate analytic models to then simulate, just the where Semianolytic comes from. And the idea being is that you can use that in order to specifically say, given a dark matter halo, you can then predict what the star formation rate should be based on off of calibrations. And so what you can then do is we can actually take an inbound simulation directly and then simulate what the line emissions from different lines are by using this. But first, the main goals before me and the density mapping community came on, the first goal of these models was just to predict the star formation rate. But then in the density mapping, we took this a step further by using codes like despotic and cloudy in order to then predict what their line emissions based on the star formation were. And so by combining both the Semianolytic models for star formation with models for line emissions, we were able to then make basically construct even maps of intensity that could potentially be used for simulations. But they also have other uses as well beyond that, which I'm going to get into. So just so this is work that was really spearheaded by my student Sheng-Chi Yang. So one of the first things she had to do was basically we had to update the calibrations, and so basically we use multiple. And so she used multiple galaxy surveys in order to calibrate basically relations between in order to calibrate and the Semianolytic model, and by that we were able to then go back and compare. Based on the line emissions that were predicted, are these consistent with different data sets? And so basically we use several spectroscopic surveys like ALMA, IRAM, and such in order to map what the line intensity of different galaxies were and see if those match with the predictions from our SAM. And so what we found was that we got really good matches between the line emissions that were predicted from the SAM versus what was measured. Of course, with the observations, they were only measuring the very brightest galaxies. That's what they do. But of course, with the SAM, we were able to predict what the line emissions would be at much lower masses that wouldn't be observable with a galaxy survey, but would be sampled by an intensity mapping survey. And so that's sort of the power of how this could help with modeling line intensity for intensity mapping purposes. Okay, so using this combined with the embodied simulation Planck multi-dart, we were able to make mocks over small areas. And so this is over just a 2 square degree area, which seems small, but it's actually much larger than the aspects area. So so it's still useful for that regard. There are ways, one thing we're thinking about is ways to expand this in the future using machine learning, but this is what we have now. And so these are just this is the sample mocks that we were able to make for this project. Note that we make not just emission mocks for C2, but also for CO, for several CO lines with applications both for Exclaim, which looking at C2 and high JC CO, which we'll talk about later, but also for CO, for low JCO like CO10, which would be mapped by COMAP. And we also made made maps for both the cosmic infrared background as well as from the Milky Way. So we can even make photons as well. So with this, we were also able to produce use these maps in to make predictions for make models for both luminosity mass relations as well as star formation rate mass relations. And so the good thing about this is that you can actually tweak the knobs for the physical properties on the SAM in order to then see how different things change. And so one thing that we map is that for example, for the star formation rate, what the values are at higher masses tend to differ based on quenching models, how you treat quenching, whereas at low masses for the line luminosity models, basically you get differences based on the stellar feedback models. And so these are knobs that we can tweak. And that's one thing that's great about the Semianolytic models is that you can actually relate this directly to physical properties like what the star formation rate is over masses in redshift. What is the emissions from what is the winds that come from AGN and things like that. And so you can And so that's something that could possibly be tweaked in the future, and in order to match with upcoming observations. We also were able to construct intensities from the SAM. So the SAM does, in fact, so the SAM is this red curve here, which the wiggles are mainly because of, excuse me, we're still trying to predict from an embodied simulation. So we have lower in number statistics, which are developing some of these wiggles here. This is something that I'm going to talk about later, how we're going to fix this in the future. But anyways, so you see the C2 here. It's more consistent with some of the models that were shown previously, that are much lower than the measurement that we had for C2. So there are knobs you can turn, but you would have to turn them really high in order to try to get something that more matches the measurement. So it's still an open question how to resolve this, but hopefully Exclaim would have something to say about this in the future, in the near future. And then also too, one thing that since we had these in volumes, we were able to also directly map statistics for these, including both the voxel intensity distribution, also known as the 1-point PDF, as well as power spectra, which the 1-point PDFs we model in the top panel with it's basically just a probability distribution function, and the bottom panel is the power spectrum. And so these are both for CO 1 to 0. And we also did some tests that show that, particularly what we have here is the red curve represents the model from the SAM, whereas the blue curve represents the Tony Lee et al. 2016 model, which also been worked on a lot by Dongwoo as well. And so what we were able to see is, although these are pretty close together in a mismatch, with upcoming surveys like Exclaim, we also showed that we should be able to discriminate between these two, at least in optimistic models of how Exclaim will be able to work. And so how sensitive it will be. So this is something that we're hopeful for in the future, to be able to discriminate between models, at least for CO. So this is, oh, sorry, just to be clear, this is for discrimination with COMAP, not Exclaim. So this is COMAP is going to map CO 1 to 0. And so we tested for COMAP that it should be able to discriminate between these two models. And so that's exciting for you guys at least. And then for all of us. And then we also made similar plots for C2, and with Exclaim, it should be able to discriminate between the C2 models as well. So how do we take this in the future? Okay, so one thing, so these are just different, so that paper, which was just accepted for publication, the goal of that was just to show that we could make these maps. We want to do things better in the future. One thing that we wanted, one thing that limits what we just show was that, with the number statistics, we were just using an embodied simulation. Ideally, what we want to do is, if we want to make better models, you'd want to not just use the galaxies that were limited in a cosmic volume in order to sample over. You'd want to use as many galaxies as you needed in order to bring the number of statistics down. In order to improve your number statistics, in order to model this effectively. And so one thing that again, this is work that's being done by my student Chung-Chi. One thing that we're working on is basically being able to make use by running the SAM on not just the halos in the survey, but to be able to just run it over, or basically be able to simulate as many halos as we need to really sample the luminosity mass relation. And to sample not just, and so really one thing that you have to account for in this is that, that this is shown by Tony Lee in his work with the CEO, is that you're not modeling just the line intensity itself. There's also a scatter that's expected, just due to properties of the galaxies that do fluctuate. And so, one thing that, and so this is something that we'd actually want to model, that we've basically been working on modeling, is to be able to model both a luminosity mass curve that also includes a scatter that you can then use later on to make your own predictions for various statistics, including power spectra endpoint statistics, as well as the 1-point PDF. And so this is something that we're actually pretty close to finishing. So right now we're at the point where we're making these predictions and for these models for luminosities based on the SAM. And so that's something that we hope to be able to publish in the next few months, knock on wood. And so, and be able to publish not only the luminosities, but also not only that the expectations out of the luminosity, but also the scatter, and to be able to use that. And which the scatter is important for shot noise modeling of the galaxies. And so, and then one cool thing about this, in particular with the SAM, is that we're going to be, since we're able to model multiple lines at once, this would be very useful for modeling cross correlations in order to in order to see how the different lines correlate with each other, and that's going to be necessary for modeling cross correlations and anything in converting those measurements to properties of the galaxy evolution. So that's something we're excited about, and there's a few papers, and so we expect to have these luminosity mass relations published in the next few months. Well, submitted for publication in the next few months, and then the further projects after that to really model the statistics in better ways and relate those and see how to relate those to science. Okay, so with that, next I want to discuss Exclaim and what we're working on. So Exclaim is a collaboration of nine institutions that are working together on various parts of the survey. So Eric Switzer at Goddard Space Flight Center is the project lead, the project scientist for the project, and myself, I'm the science lead, and we're with the rest of the most of the team is based at Goddard Space Flight Center, but particularly you have large constituents at both at not only NYU but also at Arizona State and the University of Maryland and NRA. Okay, so what is it? So Exclaim, what is it? It's a CO and C2 mapper. Okay, the acronym stands for the Experiment for Cryogenic Large Aperture Intensity Mapping. And there's a few questions that Exclaim is poised to answer. Particularly, is what factors led to the. It's supposed to help answer the questions like what factors led to the basically the downturn of star formation at redshifts less than 2. To try to get the feedback mechanisms that actually drove that. Also, one of the topics is going to be able to probe is, basically what are the abundances and excitations of the molecular gas, because C2 is a good tracer for mapping abundances of, for example, ionized carbon for the electron density in halos as well in galaxies, and it's going to be able to, and CO is a mapper of molecular hydrogen. It's going to be very useful for that. And so in particular, yeah, so the third one is to be able to map molecular hydrogen from CO, while CO10 is the best tracer of that. You can get some advantage. Exclaim will still be able to probe that by using some of the higher J lines, particularly CO 4 to 3 up to even CO to 7 6. J equals 7 to 6. Okay. Also too, and then one thing that we're going to get out of Exclaim is if we're able to do these detections with nothing else, we'll be able to have more detections of we'll be able to have detections of CO and C2 and be more confident that this is actually the signal. And with that, we should be able to discriminate between models, and that would be helpful for then seeing what the emission would be at higher redshifts, which would be useful for cosmology and reionization studies. Okay, so here we model. So this is the forecast for the statistics that we're going to measure. So these are particularly power spectra. So this is the prediction for, and the way this works is that we actually don't, although we hope to be able to measure auto power spectra, because we're mapping a relatively large area of 400 square degrees, we're actually going to be able to detect cross power spectra, and so that's what we're really banking on. The idea being that it's more with using cross power spectra, it's less susceptible to foreground contamination. In particular, so these are models of what we expect to measure for the CO 5 to 4 line, cross-correlated with the main galactic sample from the Sloan Digital Sky Survey. And this is a model of the C2 mission emission based and relative to the cross power with quasars from the BOSS survey. And so in particular, these models are based off of basically my 2012 CO model and the recent Planck measurements we had. So got to take these with a grain of salt, obviously, but that's something that we considered when, well, that's something that was considered when designing these surveys, in order to make sure that we did that always, hopefully we did that, we have a really solid chance of, particularly for C2, even if it's much lower, we still should reach a detection, and we still have a good chance of making the detection for CO based on how things work and what the actual intensity really is. Okay, so here, based on the power structure, we can then model what the constraints on intensity would be. So here we model the particularly the bias times the intensity. And what we see on these plots is basically each of these dots represent different models for CO emission, whereas these bars represent a particular measurement, a potential measurement from exclaim and what the error bar should be. And so we'd see, particularly for the lower J lines, we should see a good be able to discriminate very accurately with between different models. And we do have some discriminatory power even with the higher J models. And then here is a plot for exclaim, whereas this is what we expect. This is the error bars that were from the Planck measurement that I showed earlier, whereas this is the expected error from exclaim. And this is based on even lower emission models that are more consistent with the SAM. So when it says these are just all the lines, these are all the cross correlation power we expect to do. So the idea is that we have each of these. So for C2, we're going to cross correlate with quasars at high redshifts. With CO, we have several galaxy samples for redshifts less than 1 that we'd be able to use multiple CO lines to cross correlate with. We also have a galaxy region survey, and this is going to be important because the C1 inside the galactic plane of the Milky Way, it's a good tracer for molecular hydrogen, particularly in regions where the CO could possibly be dissociated and not be able to measure to detect be able to trace molecular hydrogen as well. So this is going to be important with doing measurement where it may not be connected with the issue. So this is going to be important with doing measuring what's known as alpha CO in the Milky Way, which relates CO emission to molecular hydrogen, CO luminosity to molecular hydrogen density. And so we can actually use that information to then scale up for higher redshift, so that we can relate our higher redshift measurements of CO to the molecular hydrogen. And again, this here, I'm just showing a map of the survey. So basically, the galactic survey will be somewhere around here. We actually haven't decided yet where the exclaim is. It's so just to be clear, it's a balloon survey. It's gonna float at about 14 kilometers, and so it's above the surface. And so so one possibility is for it to map the south. It's coincident with stripe 82. And so although another possibility is the north to coincide with Hyrax prime cam. And so there are different possibilities. We're funded for 3 flights, starting with the first engineering flight, which is going to take the first engineering flight will take place as soon as 2021, with the first science flight happening next year. And so this will be very useful for, and so this is the flights that we plan to take, and once those happen, we'd be able to do science with them. Just why, the question is, why do a balloon survey? Well, the idea is that by being able to go at very high altitudes, not at 14 kilometers, sorry, but being able to do higher altitudes at 36 kilometers, The idea being is that it's going to be at much cooler temperatures, and so it'll spread out the basically it'll spread out the line emissions coming from the atmosphere, and so it'll be good for being able to to measure intensity between the lines from the atmosphere in order to do the science we want to do. And then I just want to say also, of course, I'm also involved with Spherix as well, particularly through the CCA, although I was also a part of it earlier when I was a postdoc at JPL. And it's gonna, and in particular, it's gonna map multiple lines, including H alpha and Lyman alpha. And so the hope is there that we'd be able to use the SAM possibly to develop models for those lines as well in the future, as well as to try to use SAMs to relate spheric science in order to IGM science and ISM science. And so that's something that we're looking forward to in the future, which right now the SAM is not built yet to do IGM science. But with ISM science, that could be a seed in order to see its effect on what we'd expect its effect on IGM for IGM connections in the future. So that's that. And so now the last, I guess the last several slides would be on what we've been considering as far as cosmology connections to luminosity, to line intensity mapping. So one thing that I've been really concerned about is how we, particularly for large area surveys, which mainly will be done with 21 centimeter mapping, how do we actually do the analysis properly? And so one possibility is to do further analysis on the sky, particular if we'd want to try to have a situation where instead of doing an approximation where we look at we try to do analysis on a plane, we actually should do it on a sphere. And so, and one way to do that is to consider decomposing maps. Instead of decomposing maps in Fourier modes, you decompose it in what's known as spherical Fourier-Bessel modes. And so the idea being is a way, it sort of tries to take the best of Fourier analysis and spherical harmonics. And the idea being that you can sort of do a Fourier analysis on the sphere, where particularly a shell, where the idea is that certain modes are available to you, and so you can sample, and it's a better way to sample the matter power spectrum directly instead of through angular power spectrum, which you have to decompose out the power spectrum if you wanted to sample it directly. And so this is something I've thought about, particularly in the context of lensing. Why lensing? Well, lensing is lensing of intensity maps. Could be a powerful probe, in particular, the idea being that unlike the CNB, intensity maps don't have soak damping. And so you won't get, and so basically small scale modes will still be much available for you. And so it would allow you to extend measurements of properties of either dark energy or dark matter, or the distribution of dark matter in large scale structure. However, one problem is that one thing I was thinking about this though is that much of the work that's been done previously is assumed that you have that basically you have that you basically do this on a Fourier box. And so what I wanted to do is see like how would you actually model this in a spherical shell. And so this is something that we worked on, and so I was able to develop. And so me and a student of mine, undergraduate student of mine actually, who just started at Harvard, who's starting at Harvard soon. We basically developed a model for what the lensing should do for an intensity mapping on a shell. And so we were able to develop this. If you looked at CNB lensing before, you should recognize these symbols. But anyways, so we were able to do that, and we were able to make a forecast for Hyrax. And why we chose Hyrax is because it's a survey that's going to map basically over half the sky at redshift 3. And so we thought that that was a good test case for what we wanted to model here. And so this is basically based on the estimator we developed. This is the noise that was predicted. And so what we found was that basically, and this is the picture of the student here. What we found was that although in the box, this is what has been, the orange line curve is what's predicted in the past for the noise for each mode, for each angular mode for a lensing measurement. whereas actually we found for a sphere, you actually do at least at large angular scales, you do get a difference, a significant difference. And so this could possibly improve growth strength constraints. But anyways, we developed this, and the idea is that particularly if you consider CO55, if you wanted to measure the angular power spectrum of the Lensing maps, you could actually cut down errors by half. Although, of course, with Hyrax, it's not going to be able to measure CL55 as well anyway. With the cross correlation between the Lensing map and galaxies, you get about a 10% reduction, so not as good. But it was good to be able to develop this to have the right formalism for this, and in the future, it may be possible that you'd have more sensitive instruments which would be able to use this more in the future. Another thing that we'd want to another topic that we've been thinking about is measurements of Not Gaussianity. So in particular, as I stated in the beginning, we'd expect that with intensity mapping, since you're going to map large volumes, it'd be useful to measure Not Gaussianity, particularly because the effect from Not Gaussianity is sort of parameterized by the shift in the clustering bias of large scale structure tracers. And in particular, what you'd find, what has been modeled is that, by one of the pioneers, of course, is Neil Dalal, who's sitting here, but basically it goes as a 1/k squared. And so you'd expect to see a huge effect on large scales. And so this is, particularly with intensity mapping being able to map much larger volumes than the galaxy survey, you have the potential to be able to really move the field forward using intensity mapping. And so there's been much work that's been done on this. So I didn't reinvent the wheel or anything, but one thing I was just considering about is interlopers and how that would affect things. And so I have a student who's been working on basically how we if you have interlopers, how would that affect your measurements of FNL? And so basically what we just been modeling is what would happen to if you just tried to measure the autocorrelation to model FNL and how much interlopers would affect it. And no surprise, it's a huge effect. Totally biases everything. And so basically what we model is, well, if you use the cross correlation, how much would that reduce? Basically, how much would that reduce errors? And so what we do find is that you get a significant reduction to where you get close to where you were in the beginning. Potentially, of course, it's the best case scenario. It doesn't include, continuum programs or anything like that. But this was just a case you wanted to see. And so right now, this is something we expect to be able to finish in the next month. So I just wanted to show that. And then another thing I'm working on with another student is looking at what can we learn from galaxies cross-correlating with Cnb lensing. So this is actually not directly related. This is not really related to intensity mapping, but I just wanted to put this out there. So we wanted to. So two things we consider is we consider what constraints we would get for galaxies cross-correlating with Cnb lensing in order to probe both non-Gaussianity as well as the growth rate, which is a tracer of which growth rate in particular is a quantity you can use to probe discriminate between general relativity and modified gravity. And one thing that they've been working on is considering what you find both for if you use angular power spectra in multiple redshifts versus what happens if you use a spherical Fourier Bessel analysis in order to model a 3D power spectrum. And so this is work that he's pretty far along, and we expect to be done in the next maybe the next 6 months or so. And so in particular, we're working with the galaxy surveys we're considering galaxy surveys, including LSST for photometric surveys, as well as Hyrax for spectrophotometric surveys, I guess, if you will. So that's something that I'm looking forward to being able to present in the future. Particularly why we're looking at Cnb lensing, because we do know that's been shown by earlier work by Marcel Schmidtful that using the Cnb lensing can reduce significantly the amount of uncertainty on FNL, particularly getting it below FNL of 1, which is what you really want to look at to discriminate different inflation models. So to conclude, line intensity mapping is very uniquely positioned in order to answer questions about galaxy star formation and cosmology. And so in particular, I'm very interested in a multi-line intensity mapping campaign to do this, which is why I'm a fan of all the line intensity mapping surveys, and not just the ones I'm part of, because I think the information together will be better than just using information individually. And with the mocks the line intensity mapping mocks we're developing using SAMs, I am very hopeful that these will play a significant role in modeling emissions for multiple surveys. And so I think there will be many opportunities for collaborations with multiple surveys on that front. And Exclaim, which I'm excited to be part of, is going to believe is going to make a significant contribution for understanding CO and C2 emission, which will be helpful for understanding star formation, in particular low redshifts, how you, as well as properties of the ISM. And of course, and lensing is something I've always been interested in, gravitational lensing and cross correlations. And so it's happy to, so something I'm thinking about is how, of course, that will develop models of FNL, model of cosmology, gravity, and other constraints. And so something I'm excited to be a part of. So thank you all for your attention, and I'm happy to answer any questions.
All right, thanks, Anthony. There's a lot of very interesting work going on. So yeah, we'll take questions for a few minutes here, and then around noon, we'll transition to a less formal after seminar discussion. But yeah, I saw Wei Li raise his hand first, so we'll go to Wei Li.
Thank you very much. Very nice talk. I just had some technical question on the lensing of the intensity maps as opposed to lensing of something else correlating with them. And yeah, I thought, so when we looked at that many years ago, our conclusion was that the non-Gaussianity always dominates the error. Now, I'm not sure, because in your plot of a Hyrax, maybe you're in the regime where you're completely noise dominated, so maybe that doesn't matter, but have you thought about whether non-Gaussianity might or might not dominate that error?
Yes, so we have thought about it. So we do expect in the modeling that we did previously, we just neglected the non-Gaussianity because we're more interested in this new estimator. But we do expect it to be an issue. So one thing that we're actually considering is how the trispectrum would would affect it. And so one thing that we have been thinking about, which this is another paper. It's mainly worked on by postdoc Abhishek Maniar, which the goal is to be able to submit this in the next couple of months, because it's actually a very simple thing to consider, but it could be very useful for these type of measurements. Is to consider cross correlations for lensing. The idea being that if you have two maps of intensity, they're both going to be lensed by the same dark matter, and while at the same time being able to be rid of foregrounds, as well as at least have less foreground contamination, at least with the area.
Right. No, I'm thinking of two different things. Right.
But you're thinking about non-Gaussianity. So with non-Gaussianity, yeah, right. So with non-Gaussianity, one thing we're considering is the trispectrum and how that will affect the lensing. So
okay, just to think of two aspects of non-Gaussianity. I mean, in normal weak lensing of galaxies, an intrinsic alignment is a kind of artifact that induces a fake signal. And as you say, if you cross-correlate two different source planes, if they're far enough away, they're not going to have any spurious correlations. I don't think getting rid of the spurious correlations is an issue in practice. However, the problem is if you now ask, well, how big is the measurement noise? So you're trying to make the optimal estimator. And in the optimal estimator, that's dominated by just the self noise in each lens plane, that the variance of your power is much larger than the power spectrum squared. And so when we studied this, I guess we tried various things like decomposing it into kappa and gammas, which have their own complexities, but we claimed that does help substantially with improving optimality. Of course, it may not matter so much because for Hyrax at least, the noise level is fairly high, so it may not actually matter. But I just thought that when we thought about it, we always concluded that the intrinsic clustering it's not a small effect.
Mhm. Yeah. So we do expect, you do expect to be large. But I mean, this is something that was shown by your work, as well as work by Simon Foreman as well too. So we just didn't consider it for that previous thing, just because we wanted to model the estimator. But internally, you can also consider the non-Gaussianity as well, and how that affects it. And so that's where we're actually working on I'm working on a future paper with that hopefully will be publishing with Abhishek, where we consider this issue. In that context, though, we don't consider it for sort of a 3D analysis that I modeled here. We consider it for a 2D analysis in multiple redshift planes.
Thanks.
Okay, Abby, did you still want to ask a question? Because I saw you had your hand raised before.
Oh yeah, sorry. I think I just accidentally unraised my hand. Is it okay to go?
Yeah, and then we'll end off with Norm's question.
Okay, cool. Yeah, I just, yeah, this is really great talk. Super exciting stuff. And I was wondering about your SAM model. I think, did you say the C2 that you were modeling was at Redshift 3? And did you, or do you have plans to expand that, or did you already do that? I just couldn't, I think I
Yeah, so for the paper, we only model it at Redshift 3, but the SAM predicts it for all redshifts. And so in the next paper that we're working on, what we're going to do is we're going to publish a model of the luminosity mass relation, and we're going to publish it for multiple redshifts. Like we're going to have basically an analytic fitting function that goes with the SAM, and which you can then use for modeling statistics. And so it'll be available, and so you'll be able to see it at all the more redshifts. We do actually, so the plot that I showed earlier for this was at multiple redshifts, but it was around Redshift 3, but it can predict it for, like, so right now it could be, we ran the SAM up from Redshift 0 to Redshift 10 actually, but we only showed this because there was no way we could we didn't show maps for everything, but we wanted to show this particularly for the part that was going to be relevant for Exclaim.
Mm-hmm. Yeah.
But we do have that information, and in the next paper, we're going to publish it for the full redshift range.
Cool. That would be really awesome to see. Thanks.
I actually had a very similar sort of related question. So you've got a data point on this plot here, which comes from a paper that you were on in 2019, I think.
Yeah. So yeah, that's right. And this is this was also with my student, the same student.
Right. The same student. Okay, it wasn't clear. Okay, and then you pointed out that they're off by like almost a dex.
Yeah.
Do you not believe your model? Do you not believe your observation, or the error bar is underestimated on both?
Yeah. So I'm not convinced. I'm not convinced of the data. Yeah.
Okay.
That's why I'm not convinced of, because we're using Prink, which has broadband maps. There was the best we could do was we had to assume a model for the CIB with certain set parameters, and we had to fit those. Like for example, one thing we had to assume was, okay, we assume that the redshift revolution for the CIB goes as a power law, 1 plus z to a power.
Right.
But if it differs from that, it's possible that would mess up some of the subtractions that are done inherently when you fit the CIB and separate it. So, so we think that with a higher spectral resolution survey, we should be able to do a better job of just being able to reduce much better.
So let me go back then to your
equivalently low K parallel modes, and so
Well, let me ask about the SAM then, because you also had other plots in the SAM paper where you had individual galaxy detections on there, and you said you could reproduce those. Yeah, that plot there, for example. Yeah, right. So now, did you tune your model to fit some of these things and then predict others, or did you, how did that work? Did you tune for all the detections?
So we did not tune for these, because these were calibrated just based off of these are calibrated based on the SAM itself, to just predict the star formation rate, and so these actually happen to be for free actually.
Okay, all right, so that's actually a prediction then, those right there. Yeah, okay, and then. I mean, I'm trying to do this obviously with like fire simulations. I've got a student working on this right now, and a postdoc actually working on this right now. And the C+ seems to be pretty robust. The C0, the CO predictions from actual simulations are just way off. Basically, because if you do even a zoom simulation, you're under resolved. As far as I can tell, I think that's what's going on. And I don't believe any of Mark's stuff from Despotic or any of that. That's like, I think it's really not working very well. Again, because it assumes smooth gas distributions, and I don't think in real life it's like that. So I'm getting very pessimistic about making sort of first principles predictions of CO emission. And so I'm just curious, because I'm involved in CO map and things like that, but don't think I can actually make a believable prediction. And so I'm wondering about, I've avoided SAMs because, as you say, they got knobs in them, and you can get any answer you want, right?
Yeah.
But if
you have to believe what you're calibrating to it at some point.
Yeah, well, I mean, like originally the galaxy simulations were also SAMs, right? I mean, the claim was they weren't, but in fact they were SAMs, right? Everybody was tuning all their feedback prescriptions. With Fire, that's marginally less the way it works, but it's still got knobs, right? But if your model's actually predicting, for lower mass galaxies, which I guess is what that is, lower star formation probably corresponds to lower mass as well. That's actually nice. Yeah, okay, good, thanks. Anyway, nice results, nice work.
Thank you.
All right, so with that, we'll basically switch over to an informal post-seminar discussion. We'll stop recording, but thanks again, Anthony. It was a very, 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 very nice talk.
Thank you.